I'm happy that we have many participants despite of the less smooth way to enter the Zoom room with password and so on. So welcome everybody to the seminar on optimization. So we have today a great speaker, Jérôme Bolte from Toulouse, who has a very, very wide and a very deep research profile. He's expert in many areas, not just optimization, differential equations, geometry, and function analysis. So, and Jérôme, his research had an amazing impact on our area and introduced many important notions and many new directions to go. And today we will see something new, which is related to deep learning, but also to deep mathematics. So Jérôme, thank you very much for accepting our invitation. So we hope to have a smooth talk, and not to have the incidents from last time. So Jérôme, the stage is yours. Thank you.
Thank you, Radu. I'm not sure to deserve everything you said, but okay, thanks a lot. And thanks to the organizer for this wonderful initiative. So this is a joint work with Edouard Powell, who is also in Toulouse. Yes, so how does this work? Okay, an alternative title to this talk could have been, what does the chain rule output out of its validity domain? It's less sexy, but it is the question behind all this. To investigate this question, the talk is divided into 3 parts. First, observational part, which is quite informal. In the second part, we will provide theoretical answers. And at the end, we will study algorithms, okay? So we start with this first part. And so starting point was the training of neural networks, okay? So here you have a typical loss of a neural network. So I won't explain where it comes from. I will focus directly on the structure of the loss that we want to minimize. So as you can see, you have a sum, which is in general a large sum. And each term, the FIW, have a compositional structure. Okay, so that you can understand what's written here, I have written in blue the variables. So you have the WI, which are matrices, and which are variable of the problem, and the BI, which are vectors, and which are also variables. And so what do you see inside is an affine transformation here of some given xi, and then a nonlinear transformation. It gives you a vector, and you do that again and again, L times, which is the number of the layer, of the network. Okay, so the tricky thing in this story is this activation function, sigma. Okay, so in our case, they are defined on R, and they act on vector entry-wise, okay, like that. And a typical example that we will consider in this talk is this one, sigma t equals max 0t. That is, it is called ReLU T in neural networks. So once we have this loss, the goal is to minimize it. So we write it in a synthetic way like that, okay? And we are going to use a stochastic gradient descent method, which is a typical method for that. And this method consists in choosing a bunch of functions, fi1, fi2, compute their gradient, form the sum, and follow this sum during a short time, okay? And this is an instance of this famous SGD. But actually, it is not the gradient that we are computing. we are rather using an algorithm called backpropagation, which is computing a surrogate of the gradient. This backpropagation is an instance of automatic differentiation. And what we would like to do in this talk is to understand what it is exactly, how it works. And then when we will have a good model for this, we will try to study the corresponding algorithm. Okay? Okay, so in a few words, backpropagation is a quite simple thing because it consists in applying the chain rule to a function which is a composition of elementary function and using the gradient of each of the elemental function. So I won't enter the detail and the subtleties of a computation in automatic differentiation. I will only focus on the theoretical premises. That is, we apply the chain rule and we use Clark subgradient. Okay, and we wonder what is this backprop. Okay. Okay, so we have two ingredients to understand: chain rule, Clark subgradient. Okay. So first, this Clark subgradient or these Clark Jacobians. So we are going to work with locally Lipschitz function during all the talk. And we denote, we identify the derivative of the function to its Jacobian matrix, okay, when the function is differentiable. So what is the Clark Jacobian? Well, since the function is locally Lipschitz, it's differentiable almost everywhere. And at each point, we can thus look at the limit of neighboring Jacobian to this point. Okay, this is the definition which is written here. And we take all this limiting Jacobian, and then we take the convex envelope. This is what is called the Jacobian of F. Okay, when Q equals 1, the Jacobian, the Clark Jacobian is simply the Clark subdifferential. Okay, so this was the first ingredient. Now the second ingredient to compute this surrogate gradient, it is the chain rule. So we start with the function f, which is given as a composition of function G1, Gn. Okay, so you recall this example we have seen in the beginning on the first slide. So what we are going to do is that for each I and each x, we are going to select someone in the Jacobian, some vectors, any vector, okay? So if we look at the problem of deep learning, you remember that we had affine transformation, so it's differentiable. There is no choice in the Jacobian, but there was this ReLU function, okay, in the example. And so the ReLU function is like that, or maybe like that for you. And the derivative is not well defined at 0. And what we are going to choose is the derivative 0 at 0. Okay, so we choose this object. Okay, so, oh, what happened? So now that we have all these DGI, we can chain rule them, okay, like this, as if we were applying the chain rule, and we obtain an operator that we call DF. Well, not an operator, but a mapping that we call DF, okay? When we are in the differentiable world, this DF is simply the Jacobian. And the question for us is, what is it when we are not differentiable? So once we have this DF, in practice, what we do is that we exploit it by running a dynamical system, which is close, of course, to the gradient methods. This is what was done in deep learning. On the first page, it was this method. Okay. Okay, so now we have an idea of what is this backprobe, at least formally. It is a composition of this type, okay? And when you have ReLU, you use this derivative. Okay. So all this is are the basis, the very first idea of automatic differentiation, and I won't enter into the detail. I recommend for those who are interested the book by Grivank and Walter, which is very good. And I will just focus on understanding what is the object we have just defined, okay? I'm not interested in this talk in the process of algorithmic differentiation. Okay, so as I said, what is the meaning of this DF? Well, it is the result of a dangerous cocktail. So I recall, you start with F, you represent F as a composition, and you build DF. So there are several problems in this way of doing things. The first thing is that the representation of F is not unique. Okay, there are many possibilities to represent a function as a composition. And the second problem is that this chain ruled mapping is not in the Jacobian in general because we don't have qualification conditions. Okay, so it's a weird thing, but we want to stick to practice, and in practice they take this object and they use it. So we simply accept the two above imperfection and we try to see what are the consequences. So to have a feeling of this, we are going to go on with this observational part and look at a few examples to feel what happens. First, we play with the non-uniqueness, okay? So we take this ReLU again, with ReLU prime 0 equals 0, okay? And we form two functions, ReLU2, which is ReLU minus t plus t, and ReLU3, which is the average of ReLU and ReLU2, okay? And mathematically, these three functions, this one, and this one, are equal. These are the same function, okay? And they represent the same function. They are simply different compositions. And if you use this formal differentiation principle I just gave, you obtain different derivative at 0 for the same function, which is of course absurd, and which is due to non-uniqueness. But it's even worse, because if you subtract ReLU2 to ReLU, you obtain 0, because they are the same mathematically. And now if you differentiate this 0 at 0, you find 1, okay, because of the structure of the two guys. So even for a smooth function, with this principle, you do not necessarily recover the derivative, the usual derivative. They are spurious behaviors. And there is also an annoying thing, which is the apparition of artificial critical point. Okay, so here you have an example. You take x, you subtract 0, and when you do that, you obtain x, since 0 is 0, but the derivative of this object at 0 is 0. So you have an artificial critical point, which is not very interesting. Okay, so it is tempting to think that, okay, we have this spurious behavior, but it is because of the non-smoothness, and we don't see this non-smoothness in general. Well, it is not that simple. People tend to believe that when you make a composition like that, the non-smooth parts are not activated, but it's not true. You can make simple example as this one, which consists simply in saying that one of the function is going to send all its domain in the non-differentiability domain of the next one. And so you have to differentiate always on a non-smooth part. Okay, so you have to deal somehow with singularities. Edward ran experiments on neural networks, and we see that for networks of size, what is it, 25 layers and 8 neurons by a layer, you always activate ReLU when you take random weights. Okay, so it's not even clear that with this DF we can say that we recover the gradient almost everywhere. It's not obvious, and people have worked on this a lot. I won't discuss their work, but it's not an obvious question. Okay, and we could think then that the Clark subdifferential is not adapted to what we want to do. Maybe we can build a new operator of functions, a larger one, for which contains the Clark subdifferential, the Clark Jacobian, and which satisfies the chain rule all the time, and it will be nice. But unfortunately, and I provided actually the element of the proof, such an operator does not exist. It's not possible because of this non-uniqueness. Okay, so let us summarize this first part in which we have just observed things, okay? We have observed that formal differentiation, chain rule aggregation, does not yield a differential operator. We don't have a differential operator for that. It produces spurious outputs, okay? And we need to accept that because we want to stick to practice. And so the questions we face now is, can we find a variational meaning to this DF? And when this will be done, can we analyze the impact of the spurious behavior on static problem and algorithmic problem? Okay. Okay. So here I will assume that Q equal 1 for simplicity. And so what we want to do here is to try to find a definition of Jacobians or subdifferential in that case, so since Q equal 1, that does not use the function because we don't want to build an operator. Okay, so is it possible to define what is a gradient by itself? And yes, of course, and the answer is given by this good old Poincaré lemma, which I recall now on this slide. So you take a continuous vector field on RP, okay? And I recall you what is the circulation, which is here. So the circulation, so you take a loop, which is a curve such that on 0, 1 into RP, there is a typo, such that gamma 0 equals gamma 1. And the circulation is obtained by taking the product of the velocity of the curve with the vector field along gamma, and you integrate on 0, 1. Okay. And if you have a gradient, this circulation is equal to f gamma 1 minus f gamma 0, so it is 0. And actually, Poincaré lemma tells us that if you have a vector field whose all circulation are 0, then it is a gradient. It's actually equivalent. Okay? So this is a way to define what is a gradient without referring to the function. Okay, this is what we wanted. So let's try to see what it gives in our context. So here we consider a multi-valued mapping from RP to RP with non-empty compact values and closed graph. So it means this. Okay, for those who don't know, but given the audience, I think everyone is familiar with that. And we are going to consider such set-valued mapping which satisfies a zero circulation property. Okay, so it is a bit weird. So we are formally doing the same thing. We multiply the velocity of the loop with the set d gamma, and we integrate over 0, 1. Okay, so it is set-valued integration. And it necessitates a definition. So what is this object? Well, it is obtained by considering all measurable selection lying in D, okay? So basically you take Vt in D gamma T and you compute integral of Vt gamma dot T here, okay? And you do that for all measurable selection, and then you have your result. Here, we say that the set-valued map has zero circulation if you always find 0. Okay? And if it is like that, you call this D a conservative set-valued field. Okay? And so you define a kind of subdifferential of a function, subgradient, sorry, not a subdifferential, but a subgradient without referring to any subdifferential. And you can make the same thing for the Jacobian, but I won't develop this. Huh? Okay, so we have this new definition. Let's see how it works. So the first natural thing we want to know is, okay, it's a surrogate of a gradient, so it should correspond to a function. Well, it is the same as in Poincaré construction. Once you have your conservative field, you can rebuild the function by simply integrating over any segment. Okay, so here you take gamma, which is joining 0 to x, and then fx is equal to f0 plus the integral of gamma dot t d gamma t. Okay, okay, and you recover the formula with d gamma t equals gradient of f. Okay, so you have several forms to this writing. Okay, you can take the maximum of gamma dot tv for v in d gamma t, or the minimum, and in all cases you recover f of x. Okay, so I didn't say, but the path we are taking is absolutely continuous. Okay. So once you have a conservative field, you can rebuild the function by simple integration. It also shows you that you have a chain rule. I will come back on that later. Okay. So the function f is called the potential function for D. Okay. Okay. So let's go on, and let's try to understand what are the link between this type of objects and the object we know, which are the usual gradient and the Clark subdifferential. So you take a function which is locally Lipschitz, and you assume that you have a conservative field for f. Then this dfx is coincide with the gradient almost everywhere. Okay, so it's not very surprising. Huh? The proof blends Fubini theorem, Rademacher theorem, and a few other tricks. But so we have a natural result, okay? And with this result, we can prove an interesting and funny result. If df is any conservative field of f, then its convex envelope, so what I mean by convex envelope is the convex envelope of each dfx, okay, must contain the Clark subdifferential, okay? And in that case, the Clark subdifferential is also conservative, which is obvious to see by computation. And you see here something which is interesting. When you look at conservative fields which have convex values, then the Clark subdifferential is a minimal one. Okay. Okay, so for the moment, it's a bit dead notion because we haven't seen real examples. So let us first consider a few examples. So we have actually two classes of example as far as we understand the thing today. For regular function, f, or for semi-algebraic function or definable function, for those who know, then the Clark subdifferential is conservative. So you have two important cases, regular and semi-algebraic. For those who don't know what is a real semi-algebraic function, well, it's a function whose graph can be described by finitely many polynomial and equalities and inequalities, okay? And so we have now many examples for these conservative fields. And the proof of this result rely on basically on Whitney stratification for the semi-algebraic case. And for the other case, it is the usual regular considerations. Okay, do we have a calculus in this world? Well, yes, and it's very nice. It works perfectly because the conservative fields are defined by linearity, having zero circulation for all paths is a linear condition. And as a consequence, we have a very nice calculus. The linear combination of conservative fields is a conservative field. Okay, so when you sum the subdifferential of two semi-algebraic functions, you get a conservative field, which is not necessarily a subdifferential. And even better, when you compose conservative Jacobians, you obtain a conservative field. Okay. When I say Jacobians, it's an abuse of language. I mean that Q is not one. Okay, that's all. The word Jacobian is misleading. Okay. Okay. So let me summarize all these properties in a theorem, which is actually the one which is the most useful in practice. You take a function f that you can represent as a composition G1, Gn, okay? And you assume that everyone is Lipschitz here, and you assume in addition that the GI are semi-algebraic, okay? They are possibly non-smooth, of course. It is the objective to deal with such function. for each GI, you take a semi-algebraic selection in the Clark Jacobian of GI, okay, and that you call DGI. With this DGI, you build GG1 composed blah 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 DGM. This define DFX, okay? This DFX is not a Jacobian in general, but it is a conservative field for F. And it has this, nice chain rule property. If you take any path, gamma, and you differentiate along gamma, then you have this formula, the derivative of F gamma t equals gamma dot dF gamma t for almost all t. It's missing on the side, okay? So with this theorem, we actually answered our question about back propagation, because back propagation applies to compositional structure of semi-algebraic nature, okay? And choosing the derivative of ReLU at 0 being 0, we see that backprop is a conservative field, okay? So let us summarize all this, okay? So if you haven't listened until now, you have a summary and that a message that you can take back from this talk. The first thing is that, of course, conservative fields are zero circulation set-value maps. First point, they coincide with the gradient almost everywhere. Okay. The Clark subdifferential of regular function or semi-algebraic function is conservative. These are the basic blocks of the theory. And then we have this formal derivation principle I just stated. When you have F, which is G1 composed GM, and when the DGI are conservative, and when you do the formal derivation, that is a kind of chain rule. So here I have forgotten to write DG1, GM, DG1, G2, blah, 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 GM of X. Okay, I forgot the arguments because it's a bit heavy. So this guy is conservative. As for deep learning, we have learned that backpropagation is a conservative field, okay? Perfect. And thus, the first order mapping, which you see here, and which is used to design subgradient stochastic gradient descent, is also a conservative field, okay? And actually, this extends to many automatic differentiation process in which you just apply this chain. Okay, so this was this conservative fields. Now we are going to consider the question of algorithms, okay? So we have a surrogate notion of gradient. And naturally, we are wondering whether with this new gradient, we can make optimization. That is, we can run algorithms. And of course, we will have this question about artificial critical points that were mentioned earlier on. Okay, okay, so before considering the dynamics in themselves, we look at the critical points that are, of course, of major importance, since they will be stationary points for such dynamics. So we take a function from Rp to R, which has a conservative field, df. And we define the D critical point as the set of X such that dfx contains 0. Okay, it's like Clark critical point, but with df. Similarly, we can define the D critical values. Okay, so we take the D critical point and we consider their image through F. Okay. And now we have a third notion in that case, which are these artificial critical points. These points are critical in the sense that 0 is in df, but they are not critical for the Clark. Okay? In other words, they are these weird points we created with the 0 function earlier on. Okay? So here you have an illustration on the sign function. Okay? So the sign function is here, it is the f. And here you have a df in blue for the sign function. And all the blue dots on the horizontal line correspond to 0 derivative, which have been created artificially, but which are nevertheless present. Okay. So if we look at the deep learning case, we also have this phenomenon. It's important to understand that in deep learning, you have artificial critical point. And so this field, which is governing, for instance, stochastic gradient, is not lying in the Clark subdifferential of the sum of the function. Okay. Okay, so now we have this notion of critical point. We can look at dynamical systems. So for analytical reason and existence reason, we are going to assume that df has convex values. Okay, and we consider this dynamical system x dot t belongs to minus df xt almost everywhere on 0 plus infinity with an initialization like that. And x is an absolutely continuous curve. Nowadays, everyone knows that this type of dynamics embodies most of the properties that are met in gradient-like algorithm. Okay, so it's important to understand it. The first thing you have to realize is that the stationary point of this dynamic are the critical point. Okay, and in particular, artificial critical point if there are some. Okay, well, if we have rigidity assumption, that is, if both f and df are semi-algebraic, then the bounded trajectories of this system converge to df critical points. Okay. So here you have to realize that you can have continuum of critical points, okay? And so convergence to a single point is not a trivial thing. And for this, I'm hiding everything under the carpet, but for this, you have to prove a conservative version of the Loyazievich inequality business that has been investigated in the last decade, the last decades, even I should say. So you need to prove a projection formula, a Sark theorem, and then Loyazievich inequalities for conservative fields that are true. Okay, so it's the calculus and the asymptotic properties are very good. Okay. Okay. So let's now consider the problem, which was the one in which we were interested at the beginning of the talk. So it is about this stochastic gradient with mini batch, okay, which is a kind of discrete version of the dynamical system you just saw. So nowadays there is many work on this. I cannot quote them all. I'm just quoting the ones that are closest to what we have done, and in particular the one of Davis et al., which has inspired us. Okay, but we won't focus on classical subdifferential, but of course on conservative field. So we take a function f, which is represented as a sum, okay, sigma of fi, and for each of these fi, we have a conservative field dfi, okay. And what we are going to do with this dfi, it is, as in the beginning of the talk, is a mini batch stochastic gradient method, okay. So we draw at random a bunch of fi, okay, uniformly, and then we have a surrogate for their gradient, and we follow the direction of this surrogate, okay, and we do that on and on, okay. And the question is, of course, what is the asymptotic behavior of this stochastic method? Well, so I have just rewritten on the first line the method, and I introduce the following conservative field, which is the convex envelope of the sum of the dfi, okay? So I just enlarge convexly the sum of the dfi. Okay. Now I'm going to assume two things. First, that the steps gamma k converge to 0 as small o of 1 over log k. And second, that f is semi-algebraic, which is important for several rigidity questions. With this assumption, we can prove that for all x0, all initialization x0, such that xk is almost surely bounded, then almost surely f of xk tends to a critical value, a df critical value, and the accumulation point of the sequence are df critical points. So this result was inspired, as I said, by a work of Davis et al., which proved a similar result for the Clark subdifferential. And I would say eventually that everything works with this theory of Benaim, Hofbauer, Sorin, which explains how we can study algorithm with vanishing step starting from the corresponding dynamical system, okay? And this applied to determinist or stochastic dynamical system. Okay, so it's a nice result, but it's a bit disappointing because we don't know this df critical point, and we would like convergence to a more natural notion of critical point. And this is the object of the next slide. So here, the question we try to tackle is it possible to reach artificial critical points at the end of the process? Okay. And we will show that it does not happen in general. But for this, we need stronger assumption. Well, at this day, we need stronger assumptions. And so we come back to the problem we had in the beginning of deep learning. So you remember it was this large sum and these terms with a very involved compositional structure, okay? And in this thing, everyone is smooth, save the sigma. So we take sigma equals ReLU, as I said, okay? And for the derivative, we choose 0 at 0, as we did before. But here I have to insist on the fact that many other choices are possible. We can take more sigma. We can take things different from ReLU, like P3 ReLU. Or we could even consider more complex neural networks with like convolutional networks and non-smoothness like max pooling. So I'm just illustrating our work on feed-forward network with the ReLU activation function, but we can do much more. And so once we have done that, we go into the optimization phase, which is this, and which works. So I think should be 1/q here. There is a typo. Okay. And so we run this this method, and we know at this stage that conditionally to the fact that the sequence is bounded, we will reach the critical point. But it's even better in that case, and it will be my last slide. We can show that there exists a finite number of steps, f, and zero major subset n of initialization, such that if I take a positive sequence in small o of 1/log k, avoiding values in f, if I take an initialization in x0 out of n, sorry, then I may say that conditionally to the fact that my sequence is bounded, that gxk converge towards a Clark critical value, and the xk converge towards a Clark critical point. Okay. So here we are somehow happy because we addressed the problem we were trying to solve at the beginning. But many things remain to do, and in particular, it would be very interesting to understand if we have actual convergence. So we are working on that with a postdoctoral researcher, Rodolfo Rios-Zertuch, and he provided new ideas using closed measure and showing that the behavior of these dynamical systems are very complex, and obtaining convergence and convergence rate will be very difficult. Okay, so I think I'm done. So here are a few references. Okay.
So thank you very much, Jérôme. Very nice talk. So as I announced at the beginning, deep learning and deep mathematics. So it's time for questions. So then, yeah, let us do as follows. So please ask your questions in the chat, and then I will unmute your microphones, and you can
so I don't
interact with the speaker.
Yeah.
So then probably, yeah, I can start. So you mentioned at the end.
Yes.
Okay. Yes. So you mentioned that you are trying to prove the convergence of the whole sequence, like let's say global convergence. Mm-hmm. And so would let's say critical service techniques help here?
No. They are not enough.
They're not enough.
No, they are not enough because you have crazy oscillations, and it's not enough to control the sequence. And Rodolfo has maybe built a counterexample in which you have a function which has this property, and you don't have convergence. So you need more rigidity than this.
Okay. So we have some questions. So let me. Okay. So we have two questions from, I guess, from Patrick Combet, PLC. So the first question is: boundiness is usually hard to establish. How do you deal with that?
Well, I don't deal with that. It's true that it is very difficult, and I don't know. Actually, I don't know how to do it. And even if we have a coercivity assumption, I'm not sure that we can so easily say that the sequence is bounded when we have this stochastic approach, but maybe it's possible. So let's say that out of the classical coercivity assumption, I have no idea of.
Sure.
Yeah, I don't know.
So same story with boundiness. It's not easy. So second question from Patrick: did you consider deterministic rather than stochastic sweeping of the indices?
Yes, it will work the same. We did not write it formally, but yeah. So for us, the goal was just to understand this stochastic gradient with mini batch, and this is why we and the back propagation algorithm. It is an algorithm, but many things remain to do, of course. And I think that for the case Patrick is mentioning, it should work also.
Okay. So Defeng Sun.
Hi. So hi, Jiahao. Long time for no thing. So here's the question. You talk about this Clark-Jacobian at the very beginning now for ReLU problem, right? So for the deep learning problem based on ReLU. So if you look at the function involved, it is a piecewise smooth function, locally limited continuous, right? For this class of functions, because it's very late in Hong Kong now, I can't remember exactly. For this class of functions, is this Clark-Jacobian almost surely equal to the gradient of the function when it is, okay, when it's differentiable. Of course, Clark-Jacobian may not be the only element of the Jacobian, right? But the Clark-Jacobian may still be the same as the single element of the Jacobian, almost surely. I think for piecewise smooth functions, just as a function involved the ReLU problem should be true. So for deep learning problem, maybe that's why, okay, you have new theory to explain that, right? But if you look at the piecewise smooth functions, maybe it's still okay for the Clark-Jacobian to be a singleton, almost surely. So I can't recall exactly I'm right or wrong, but I think there are some results on this part. Yeah,
I think you're right, but I don't understand why you say that, because after you have to compose them together, and this is where the problems happens.
Yes, if you compose them together, then it's not true. May not be, let's say, an element of Clark-Jacobian. But in theory, so the measure that the Clark-Jacobian not equal to the single element may be zero. That's the statement.
Actually, we proved it. It was sorry, where it is. Okay, this theorem that you see here.
That's one-dimensional case. What I'm talking about is piecewise smooth mappings, not about the piecewise smooth functions.
Okay. Okay. So
I can't recall exactly. Maybe the question maybe can help for your thing. I can't recall exactly, right?
Yeah. But
theories, of course, can solve semi-algebra theory, can solve the issue already. Okay.
Yeah, but it works. I think you say. Yeah.
Okay, thank you. And I'll see you here online.
So Joydeep.
Yeah.
Joydeep.
What?
Joydeep, you had a question? Not anymore. Andre Souza has a question. Andre Souza. Okay, then yeah. So you're
Yes.
yeah.
First, I'd like to thank you.
Can you speak louder?
I would like to first thank Professor Jérôme for the good talk. And my question is about the Poincaré lemma. I find it very interesting. And the conservative field, I'd like to know, is there a bibliography?
I don't hear you.
Okay, okay. So probably your mic is not working very well. So then let me read your question. So the question was, did you define the conservative field for the first time, or is there a bibliography already?
We had the feeling, that it was new, but we never know. Maybe in the USSR, I don't know, or in another civilization. No, I don't know. We had the feeling it was new. Yeah.
But of course, there was an intuition coming from Poincaré lemma, and yeah.
Yes, so everything, comes from there. Once you understand that you cannot expect to work with an operator, you have made a great step. So it's an operator-less approach.
So we still have a question, Joydeep. I will okay, unmute your microphone, and you can ask the question.
Yeah,
okay,
is the last result, Jerome, for only for dynamic case? So this last result, the last one, last slide, the last slide. These are all for the dynamic problem, right? With the time variable, the one which you had.
It's discrete. It's discrete, this one. So it's a stochastic gradient with mini batch. This one.
Okay.
So the DFI1 is backprop.
Okay.
Backprop of FI1, backprop of FIQ.
Now I that almost surely part I wanted to understand. Okay.
Okay.
Yeah.
Aris has a comment. So Aris, I mean, I will now unmute your mic, or you can do it by yourself. Yeah. So yeah. So Aris, if you want to comment. Oh, so we have two more questions. We have one comment from Aris. Aris.
Yes. Okay. Yeah. No. It's just a comment that this notion of appears in a completely different setting recently to the theory of Banach spaces. I mean, to define the free space of Rn, of a space of finite dimensions, then essentially you have a bounded function and a bounded operator from Rn to Rn, which is in L infinity. You assume bounded, not locally, globally, and then you are looking for the cases which this function comes as comes from a subdifferential of a function from Rn to R, and this appears. I mean, it's recent work last year, I think, or 2 years ago. By the way, my master student Gonzalo Flores did this in his master thesis. I see the setting is completely different, right? It's just in theory, in function analysis. But this idea, I mean, not under this name, but this non-smooth Poincaré stuff appeared there as well.
Interesting. Yeah. It's true that it seemed interesting to look at the object as a functional object. I don't know what you did with it, because I don't know what are exactly these free spaces, but yes, I feel it can be interesting.
So there is another comment, Jérôme. Could you please comment a bit on the convexity of DF?
comment on the convexity of DF. Well, we use the convexity of DF in this method because we need an existence theory for this differential inclusion. And to have an existence theory for this differential inclusion, we are using results that rely on convexity, compactness, and graph closeness. Okay. And so when we study our algorithms, since we compare the algorithm to the continuous dynamical system, we also have the apparition of a convex conservative field. Now, is it possible to remove the convex envelope here? I don't know, maybe. But we did not work on this because we wanted to get rid of many more things, all artificial critical points. And so we wanted to have results on the Clark subdifferential, which was the last slide. And so we were happy with that. I don't know if I answered the question.
No, I think so. Yes. I mean, yeah. So then let us stop here. Thank you, Jérôme, for the nice talk. Oh, there is another question. Okay, I have to ask. So Anil Tanvani. So you can ask your question by yourself if you want. Just unmute your mic. Otherwise, I can ask a question. No, but okay.
Yeah, sorry, I did not unmute myself. Thanks, Jérôme, for the nice talk. I just have a question about the object DF that you have defined. So if I understand correctly, this is not uniquely defined for a given F, right?
Yes, exactly.
Okay, yeah. And so if I have an F and I want to compute DF, would I run into computational issues? Let's say if my algorithm would run into computational issues, or have you considered these kind of questions?
Yes. So what is hidden again below the carpet is that this automatic differentiation does not act on function, but on programs. So okay. so you don't differentiate a function, but you differentiate a representation of a function.
Okay.
You have G1 composed GM. Okay, and this is the object you differentiate, and this is why there is not only one DF, and this is why it is not an operator. Okay, so what you have to understand is that if you want to use this theory, you have to fix a compositional structure. And with this compositional structure, a choice of derivatives in the Jacobians, and then you can work with this, and you have a well-defined DF, which is obtained by kind of chain rule, by chain ruling the DGI.
Okay.
Is it what you wanted to know?
It is indeed in the direction where I was asking where I wanted to ask my question, but I have to look more into it to understand more about how to use these things. So thank you.
Thank you.
So thank you. Then I propose to stop here. Thank you, Jérôme, for the great talk.
Thank you.
So and a very nice discussion. Everything was stable. Yeah? So this is nice. So we will have the video and the slides on the website of the online seminar if Jérôme agrees. And thank you. And next week we will have a joint talk with the seminar in games theory, and the speaker will be Panayotis Mertikopoulos. So I wish you a nice week. So thank you, Jérôme.
Thank you.
All the best, and see you next Monday.
Yeah. Bye bye.
Bye bye.